Hello everyone. Hello. Hi Ravi.
Hello, Bhumik.
Let's give it a start. Let others join in. Let me share my screen. So until yesterday, this is what we have looked into. We quickly revised the basics of SVM. Then we have fit an HVC. Okay, we have fit a support vector classifier. Okay, and there we found that the model that we have created is not so good. Okay, but we have options to improve it. We can do grid search, cross validation, and so on and so forth. But before we do that, I just wanted to quickly show you something. Is this if I go to the documentation of sklearn, there's something that I want to specifically mention here, which is related to this part because this is where a lot of confusion usually comes. So one important thing to note over here, other than the other hyperparameters which we have, right, is this thing, which is the kernel. Okay. Why I am specifically mentioning this is because this value basically refers to the kernel trick, okay, which the model, let's say, which the model uses. Now, because we have used this one, right, we have just imported SVC. And in our initial model, let's call that M1, we did not specify any values of the hyperparameters. So obviously, it has taken up the default values. Right? So it has taken up the default values of this kernel variable also. You can see there are a lot of options over here. So let's try to understand what these options are. The first option is linear. Okay, this is the most simple one. And this is what assumes that if I have a data, then my data is linearly separable. I have one class over here, let's say, and I have another class over here. And hence I can draw this kind of a hyperplane. So my hyperplane can actually be a straight line. Okay, just imagining or assuming here that I have two features F1 and F2, I can draw a hyperplane which is actually cutting it through, right? Of course, it is going to have the margins also, right? And this is going to be the width of the margin, let's say, but the hyperplane is going to linearly divide the data. This is almost similar to what we have seen in case of, let's say, logistic regression, right? This may look similar to the decision trees also, but in case of decision tree, what we had done is that we created something known as hypercuboids. Right? If you remember, we created something known as hypercuboids, and it was to divide the data into sectional areas like these. Okay, so we did one break of the tree, it created this. So this is the first break of the tree. This is the second break of the tree. Let's say this is the third break of the tree. Right. So these are kind of spatial areas, right, that we have created. They are in spaces. They are in let's say dimensions. So that's the reason why uh, we commonly call that as a hypercuboid. It might look similar to what we can see over here, but technically it is not, right? Because this hyperplane can be represented by means of the equation of a straight line, right? So uh, this is the option which is given by linear. However, linear is not the default option. If you see, the default option is RBF. Okay, the default option is actually RBF. RBF is where, okay, RBF is where, let's look into RBF once. Okay, RBF is actually something which we have already seen, by the way. RBF is the one which we took example for. So yesterday or the day before yesterday, when we did the session, we looked into a scenario which is something like this. So we were able to divide this kind of elliptical shape, or we were able to convert our 2D data into this kind of a elliptical shape, right? We are able to do that, and then further what we did is, right, we created the decision boundary which was, let's say, somewhere over here. Okay, not a very good drawing, by the way, but I think you are getting the point. So the decision boundary is somewhere over here. Okay, the boundary is somewhere over here, and this is my hyperplane. Okay, this is the hyperplane, which is dividing the data very, very well. So whatever is on top belongs to, let's say, one class, and whatever we have at the bottom is actually belonging to another class. Let's say that is B. It's kind of a setup where we are actually creating an elliptical shape in n dimensions. In this case, we created this third dimension, which is z, and we applied a function on f1 and f2, where f1 and f2 are the two features on top of which we initially tried to plot the data. And if you remember, the initial plot looks something like this. The initial plot, what we saw earlier, it looked something like this. We converted this two-dimensional plot where x-axis was feature f1, y-axis was feature f2. We converted this into this three-dimensional plot. In this case, n is equal to 3, right? And we got this kind of a shape. So this is what by default, okay, by default, sklearn's support vector classifier is going to do, right? We have two more options here. Okay, one option is related to polynomial, and one option is related to sigmoid, and then there is a pre-computed. Okay, pre-computed can be gotten out of the way because pre-computed is something which we seldom use unless and until you are a very good mathematician and you understand what kind of functions you would like to model using your data. Because this is like using, this is like using a custom function in Python. Okay, so imagine that you have written some custom function in Python fn1. Okay, and then you are calling it inside some kind of a lambda expression. Okay, so this custom function is going to do the modeling of the data. It's going to do the transformation of the data, or we can also say, basis our understanding, it's going to do the changes in the point of view of the data, right? Pre-computed is something which people use. I'm not saying that people don't use it. Okay, although I don't use it. I don't use it because I'm not really a mathematician. I understand some part of math which is going on in the background, but I'm not really a qualified, let's say, mathematician. If I had been, or if my area of work was more into research, right, then I would have tried to play around with this, right? The rest of the two options is polynomial and sigma. From the name only, you can clearly understand what is happening. Polynomial is something you convert any equation in nth order, right? So polynomial, let me just clear the drawing. So polynomial is going to, let's say, a polynomial graph will look something like this. So if you, right, in this case, how many peaks do I have? I have a peak here, I have a peak here, I have a peak over here. So I can say this is polynomial of degree 3, right? I hope I'm right. This is always a confusing thing, but polynomials always has a degree, right? Always has a degree associated to it. This is also similar to what we can do in case of non, or what we usually do in case of non-linear regressions. Okay, in case of regressions, it is not always the case that I'll have my data points which will be so well structured, right? Let's say this is just an example where I have two variables, age and weight, right? Age and weight are two features, and I'll have a straight line. Let's say I'm going to have a straight line which is going to be my decision boundary, and the decision boundary is going to look something like this. But this is uh, often this is not the case, right? This is not the case with complicated data. If I have complications in the data, this is not going to be the case, because this is a very, very simple straight line which can be given by the equation y equal to mx plus c. If that is not the case, if I have a different kind of situation, I would like to model this in a better way, then maybe I can use a line which is something like this. Right? This line might look like an overfitted line at the first place, but this is basically polynomial regression. Right? We do sometimes use polynomial regression, not as much as linear regression, because linear regression, by its architecture or by the design of linear regression, it is very easily explainable. Right? But polynomial expressions are going to be something like this. Let's say ax cube plus bx the square plus cx plus d. Now, this x cubes, let's say this is x1 cube, this is x2 square, this is x3, right? And then there is some kind of a constant which is involved here as well. You can call that, in this case, let's say the constant is something like this, which is passing through this line. Let's say this is -1 value. So d becomes equal to -1. And then the a, b, and c are the slopes of each and every features. Now, if x1 is a feature, let's say x1 is a feature which is, I don't know, let's say the salary of an employee, let's say, right? Or maybe it is going to be the square foot of the house for which I'm trying to predict the rent, right? Then x1 represented as x cube is very difficult. In the same way, polynomial fits, if we are going to do, In that case, the degree is really going to determine. Higher the degree, more complex the model it's going to be, right? Now you can say the same thing for RBF also. You can say the same thing for RBF also, and that's one of the, I will not say drawbacks. I'll not say drawbacks of SVC, but this is like it comes out, or it's going to come out of the box for any SVC implementations. Even if you're doing it out of your own hand, if you, let's say, read the paper and try to do a custom coding, okay, if you try to do a custom coding for SVCs also, you'll come to know that explaining an SVC is really very difficult. Right? There are few ways in which we can explain SVCs, okay, especially when it comes to linear, okay. But for the rest of the cases, it is really difficult. But the that's kind of a balance, I would say, that we'll have to maintain, because more often than not, if I have good logic, or if I have, let's say, pattern inside my data, okay, if I have collected good data, I've prepared it in the right way, and these kind of complex functions like RBF is actually going to give me higher accuracy, okay, higher accuracy it is going to give me, okay. So that's the advantage actually. That is actually the advantage of using it. Okay? Or otherwise, plain and simple, we can use linear. Now, when I'm using linear, I can not only use SVC function, or I can call this SVC from sklearn, or there is one more option which is called linear SVC. Okay, you can use any of them. It is the same thing. You call SVC pass the kernel value is equal to linear, or you call linear SVC. Both are going to do the same thing. No issue, right? Other than that, there are many other things which is C and gamma. That's the most important thing. We have already covered this briefly earlier. Okay, we have already covered this briefly earlier, but let me also quickly tell you what these are. These are the most important hyperparameters, which you can simply say they determine. I can say they are going to determine how complex, okay, the model, okay, model's learning, okay, learning will be, right? Now, C is the regularization parameter, and gamma is the kernel coefficient. Okay. Now, as the gamma increases, if gamma value is high, okay, if gamma value is high, what is going to happen is your area that you are cutting out of the data. Let's take a very, very simple example. Let's take a simple example of where, let's say, I have data which is something like this. Okay, I have data which is something like this. Now, I can create a linear SVC over here also. But let's say I have come up with an SVC which is giving me two decision boundaries like this. So it is splitting my data into higher order functions in this two way. Now, this is a very good estimation. If you look at the diagram itself, you can see it is a very good estimation. This indicates a very high value of gamma because it is the kernel coefficient, how the kernels like RBF, polynomial, or a sigmoid, wherever they are used, okay, they are going to create the decision boundaries. They are going to create the decision boundaries in this way. Right. So this is good news that I have done the estimation in this way. But this is clearly it looks like overfitting, right? It looks like overfitting because it is both of the classes are really very well identified. I've not deliberately drawn them into three dimensions. I'm just to simplify my example, I'm showing it in two dimensions only. But this kind of a representation, right? This comes into n dimensions. When we convert this 2D data into n dimensional data, this kind of a decision boundary will get created, okay, by means of the hyperplane, right? Which the model is going to come up based on the value of gamma which you give. And in the same way, the regularization is also going to work. How much you would like to penalize, okay, how much you would like to penalize the model in case it is overfitting or it is underfitting, right? How much you are going to penalize the model. So the most important two things, or the two hyperparameters which are of primary importance, I would say, is first of all the value of C and then the value of gamma. This degree is optional because degree only comes into place if you have a polynomial kernel. And of course, we will need to play around with the kernel parameters also. Now let's quickly see if there is any way in which I can explain my model. Now there is one way, okay, there is one very, very easy way in which I can explain my model. This is as simple as coefficients. These coefficients are nothing but, let's say, you have a multiple regression kind of a problem where you have beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus some error, right? I'll just ignore this error for some time and this intercept for some time. The rest are the slopes, also known as the coefficients, right? Clearly, let's say if this y, this will say the selling price, okay, the selling price of my house. X1, let's say, is the size of the house. X2, let's say, represents um, how distant it is from the highway, right? And X3 is something else. So, or maybe X3 is let's say, a categorical feature which says, do we have hospitals nearby or not, right? So, do we have highway or how much is it distant from the highway? Do we have hospital nearby or not? And size. So, these are the three features. Let's say you have X1, X2, and X3. Okay, these are the three features which you have taken to model your data. You are trying to predict the selling price. This is clearly a multiple linear regression problem, right? We have already seen an example like this when we took the Boston housing price example. Now the point here is, if B2 is highest amongst B1, B2, and B3, then we can say that distance from highway, right? This is a very, very important factor or feature in determining the selling price of. It may well be the fact that from my model, I find out that more my house is closer to the market, which means it is farther away from the highway, the house price is going to increase, right? Or it can be the opposite also. So this coefficient is a very good thing, which is basically an ND array, right? And I can find the weights assigned to the features or the coefficients of the primal problem. The only problem here is, only limitation here is, obviously it is available only in case of a linear kernel, because in case of a linear kernel only I'll get an equation like this. If I don't get an equation like this, how am I going to find the coefficients, right? That's the reason why. Okay, that is the reason why if I'm using anything like RBF, radial based function or radial basis function, or like the polynomial equation, okay, or any custom function or any predetermined kind of a function, right, or any sigmoid function, okay, then it becomes very difficult for me to explain my model, right? But obviously, if I have very complicated kind of a scenario later on, as I told you in the last class also, in case of deep learning, we will see an area of application which is CNN, where we will be using support vector classifiers also, right? In that kind of a complicated kind of a scenario where I have to work with images and find out the details inside the images, then SVC is going to come handy, right? In which case I'll have to use something like RBF or Poly or something, right? In which case I may not be able to use linear, right? In which case I'll not be able to explain the equations, right? So I can say this is the tip of the day, right? This is the tip of the day where people are not expecting you either. You are not expected to explain the model, or you have already done EDA to the death that you are able to explain the current scenario very, very well. In this cases, use SVC without any doubts. But also keep this in mind. I've already informed this in the last class also. N and D. D is the dimension of the data, N is the number of rows of the data. If N is higher, it is going to be a problem. If D is higher, it is not a problem. So if D is higher, go ahead and use SVC. But if N is higher, okay, it is going to be a problem unless you have very good CPU, unless you have very good infrastructure. Okay, so keeping that in mind, you can try to find out where I'm going to use SVC or where I'm not going to use, right? So keeping this in mind, let's try to find the best values. I'll just keep this page open so that I'm going to refer to it. C is a float value. So let me just come over here. I'm going to say from sklearn dot model selection, if I'm import grid search CV k fold first, and I don't even need a k fold because I'm not implementing it. So now what I'm going to do, number of folds, I'm going to say folds, number of folds is going to be, let's say 5. Okay, and then my parameter grid, This is going to be something like this. This is something which we have done earlier also, so it should not be an issue for us to understand. Now, C can take any floating point value. So let me start with 0.001. I'm going to say 0.01, then I'm going to say 0.1, then I'm going to say 1, and I'm going to say 10. Okay, I can even go up to 100. Right now, the next value I'm going to take is the gamma value. Let's do one thing. I'm just going to take the same thing over here, right? And the third thing I'm going to take is kernel, and I'm going to play around. Okay, I'm going to play around with linear, and RBF is my default. So why not also play around with RBF? And I'm going to play around with, let's say, sigmoid. All right. Let's say these are the parameters that I would like to play around. Now I'm going to create a variable called grid search. This is equal to be grid search cross validation, where estimator is my first model that I have created. Where is the model? SVC1. Okay. SVC1 is the first model that I have created. Then my number of my cross validation will be dependent on the number of folds. So my parameter grid, okay, param grid is going to be parameters. Okay, I'm going to say verbose is equal to 3, and I'm going to say n jobs is equal to -1, so that it uses all my power of my CPU and so on. And then I'm going to say grid search. Okay, it's fine. Grid search dot fit extend. Okay, y. Okay, now that I am fitting it, there are total 375 fits it is going to do. Right, it is going to do 375 fits. Okay, let's see how much time it takes. Okay, it is already processing, as I can see in the background. It does not show the outcome here. So let me just do one thing. Let me just stop sharing, and I will show you my Anaconda prompt window. I hope you can see it on the screen. So the verbose outcome is coming on my Anaconda prompt from where I've opened the Jupyter notebook, right? It is coming from there. I don't see a very good score. I really don't see a very good score there. I see the score is oscillating within that 40 to 70 kind of a range. I don't see any further accuracy improvement in there. There is a reason behind it also, right? We already know that we have a data which is not really properly distributed when it comes to the outcome variables, right? So that's the reason why there may well be such kind of a case, right? So let's wait for a few more seconds. Already 272 models are fit. Just wait for some time. Let this complete, and then obviously we are going to do grid search, not best estimator, and it is going to tell us the parameters that we need to use. Okay, only the parameters that it was able to find, which is going to give me good accuracy score. So by default, as we already know, we have seen this earlier also, by default it is going to use accuracy as the measure. It does not know, right? This function is not aware whether my data is uniformly distributed or not, or whether the number of samples which I have as part of my outcome variable, they are uniformly distributed or not, right? So you can also change that. There is a way to change uh, the metric which we would like to use to do the grid search. So we can also change that, but let's stick to by default things right now. It's trying to fit the model, and at one point in time it has gone really slow, and that's what I could see in the background, where C value is 10, gamma value is 0.01, kernel is linear. When I have a linear kernel, it's stuck over there. Okay? My model is actually stuck over there. So what I'm going to do is I'm going to cancel this. I'm going to interrupt the execution because I don't want this to continue for a longer period of time, so that we don't waste time. So it is very clear that when I select linear value, it took a lot of time. Okay? It is really taking a lot of time. If you would like to see, I can also quickly show you. Give me one minute. I can also quickly show you. Let me just do a new share. I'm going to share my window. Here, it came to this place. C equal to 10, gamma equal to 0.01, and then kernel equal to sigmoid. Okay, score was something like this, which is okay. Let's ignore it. But the moment it came over here, right? The moment it came over here, kernel equal to linear, gamma equal to 0.1, c equal to 10. It was taking a lot of time, and that is where I did the interruption of the kernel, right? So this is an indication that linear is causing my fits to be slow, which is not a good sign. It means my data cannot be modeled linearly. So let me just remove that. Okay, there is some error. Is key locking moved one? Okay, let me fit this. Let me try to see how it goes. Okay, I think I may have to restart my um, notebook also if this does not work because I interrupted the session, right? But let's see, it is going to catch up. Any questions in the meanwhile? If you have any questions, please do let me know.
No questions as of now.
It's taking some time. If it does not run, does not start, let me just do a restart and restarting the kernel. Okay, I'm doing a run all. I don't think it is working as expected. I may need to stop this and restart this because shut down the kernel. Let me just shut down the kernel. I'll interrupt the kernel and then I'll try to shut it down. Yeah, the code should be there. Code should be there. I expect the code not to go. Okay. So let me see if this. Yeah, somehow it started executing it again. Good, good. For some reason it got stuck and now it is executing. It has 250 bits. Okay. Now let's see. This one should be faster because I have not taken linear. Taken the rest of the kernels. It should be faster. And it is done. So if I do a best estimator, it is telling me c equal to 10, gamma equal to very small value is going to do the trick for me. It is going to be better. Okay, let's see. So I'm going to call this SVC underscore 2 and I'm going to fit the model like this. Then SVC underscore 2 dot fit. I'm going to use the training data and I'm going to fit my model and then I'm going to say ypred 2 is equal to SVC underscore 2 dot predict, right? And here I'm going to give the test data and then print classification report y test, sorry, yeah, y test or y spread 2 and y test, right? Now I see somewhat better model, not really very, very good, but at least the values are somewhat more, but it's not that much good. If you look at this, the accuracy score, y spread to, although I should not be looking at the accuracy score at all. It is not a justified thing here in this case to look into accuracy because I have clear case of class imbalance. I should not be looking into it, right? So just for the sake of doing the same things that we have done earlier, uh, I'm just continuing with the flow, right? Here also I see a lot of misclassifications are done. How do I identify this? Let me just quickly tell you. How do you identify from a confusion matrix that we have done misclassifications in the model? There's a very, very easy way. Try to look at the diagonal elements. Okay, if you look at the diagonals, these are the correctly classified points. If you have a multi-class classification kind of a problem, right? So you can clearly understand how many correctly classified points are there. So it is like 147 plus 109 plus 2 plus 0 plus 0 plus 0. I'm not going to write this. So this is going to be what? 147 plus 111. So it is going to be 258. 258 are the correctly classified points, and incorrect classified points are these. The ones which are not there in the diagonal. There are a lot you can see, right? So it is like uh, here also, this one also, right? So I can see 67, 67 plus 94, mm, 67 plus 94 plus uh, 61. These are the incorrectly classified points. Okay, 12, 6, 12, 13, and 9 will be 22. So 222 incorrectly classified points are there. This is really not a very good model, right? This is really not a very good model. That is going to happen. I mean, there is nothing wrong in this. In our model, this is going to happen because we have a class imbalance. So let's try to see if we can do something about class imbalance. Yeah, that is something which I wanted to cover today. Okay, that is one way in which we can take care of this. Okay, one way in which we can take care of this. There are many other ways. Okay, one way which I like doing is because this implementation is very easy, understanding is also very easy. There is a technique which is known as smoting. Okay, there is a big name behind it. Okay, if you want, you can go through it from the documentation. There is a big name. The abbreviation is very big. Okay, but what it is going to do for us is that it has two functions. I'm going to call any one of them, and it is going to work accordingly. Two functions it has is called upsampling, okay, and down. Usually, what we do is upsampling. Upsampling is where, okay, let's say I have a data set and I have a class distribution problem where I have this target label. Okay, these are my features, let's say. Okay, these are my features, and I have this target where majority of my entries, okay, majority of my entries are 0, 0, 0, 0. Only one entry is 1. So let's say I have only 5 observations, n is equal to 5. I'm not going to consider the dimension of the data. Okay, I'm not going to consider the dimension of the data right now because it doesn't matter. But I have a problem. 80% of my data, you see, 80% of my data belongs to one class. Only 20% belongs to the other class. Okay. So you might be wondering in what kind of cases this is going to happen. This is actually a real case. Okay. I'm actually not supposed to share the data with you, but this case is real. This case is where I worked on an analytics related to fraud. We have a system in our office where we wanted to find out how many fraudulent transactions are happening. Okay. Then there was another case where I wanted to find out if there are any SLA breach which is going to happen. Okay, if there are any SLA breach which is going to happen for any incidents, for any tickets on which our operations teams work. Okay. In that case, also the breaches or the faulty cases, right, the ones which we are trying to avoid, right, is only 10 to 20% of the data. Okay, that's the good news from one perspective. This is good. Okay, this is a very good news because I have lesser such cases. I have lesser number of frauds. I have lesser number of breach, which is okay, right? But from the analytics perspective, this is bad, right? Because I have only one sample out of 5 samples for this data. So what upsampling does is, this is my favorite technique. This is what I'm going to use over here. Upsampling is where I'm going to take this features over here. Let's say there are 4 features. Okay, there are 4 features. Okay? So dimension of the data is equal to 5. Let's say there are 4 features, right? I'm going to take this row and I'm going to duplicate it. Okay? I'm going to duplicate it. Now, this might sound really weird because I've taken an example where I have only one such row. But if I have a data set where, let's say, I have 2 classes, class A and class B. Class A, I have 200 instances. Class B, I have 50 instances. I can take randomly 10 instances out of these 50 instances and try to duplicate them. Okay, 10 times each. Okay, which means I'm just trying to duplicate the data, or maybe 3 times each, right? So 3 multiplied by 30. So 30 times 30 rows, 30 rows, 30 rows. So I have now 30, 30, 30, and 30 rows, right? In this way, what I'm just trying to do, I've just created 120 artificial rows, and I already have the 50 rows. So 120 plus 50, now I have 170. I can try to generate one more, right? I can try to generate one more. Now 170 plus 30, this is going to become exactly equal to 200, right? This is what is happening in case of upsampling. I'm just trying to upsample the class which has less frequency, right? By randomly picking up rows and duplicating them. Now the duplicate may not be exact same kind of a duplicate. It may not be really kind of a copy paste that we are doing in a notepad or in an Excel sheet. It may well be the fact that the algorithm in the background is going to take a range of the data, is going to understand the distribution of the data, and then accordingly, it is going to generate random values of the features which are falling within the distribution of the data. Right? I leave that up to you for you to study. Okay, I'm going to put a link in our uh, portal from where we should be able to study more about SMOT. Okay, how it works internally. This is a very interesting thing it does, right? But upsampling is something which we very commonly use. Okay, let's try to see how it can be done. Okay, let's try to see how it can be done. So what I'm going to do, give me just 1 minute. I'm going to open this window over here, and I'm going to say IMB learn smoking. Okay, so there is already a blog like this to tell you that that is not an issue. So in this blog, I believe I'll get the examples which I am looking for. This is an excellent blog. I'll just ping you here also. I'm going to ping you here also, and I'm going to share this on our portal as well. Okay, upsampling is what we are going to do. For this, you will need a library which is imbalanced learn. Okay, if you don't have this library, you will have to install it. So let me just see. I think I have this library. If I just import, it should not be giving any errors, which proves that I have the library. And then I can go ahead. Let me see. It's taking some time today, most probably because there are other applications which are open. Yeah, IMB Learn is there. So let me just try to take an example from here. That is a very, very simple example which is given over here, so that I don't have to uh, do anything. So this is what it is doing. It is taking an oversample, a dot fit resample. Okay. So if you do a fit resample on our X and Y data, you get our data. If you do a fit resample kind of a thing, you will get the revised kind of a data. Let me just see if there is anything else which these guys are doing. I don't think so. There is a sampling strategy concept also, but it's something which I don't want to explain right now. Okay. Sampling strategy is something how it is going to internally, pick those random rows, right? So let's see how it is going to do. So yeah, I think that's the way. So there is nothing else which we are doing. So let me just again validate. Fit resample is something that I need to do. So I'm going to say xy is equal to or I'm going to do something like this. Let's say oversample is or smote is equal to I think from IMB learn I have to import smote or otherwise how is it going to work? Give me 1 minute. Yeah, let me see. Okay, documentation seems not to work. Okay, import IMB learn smote is equal to no, yeah, smote is not defined. So that is what I was saying. How am I going to get smote? Let me look at something else. Sklearn smote. This should also be there. Yeah, smoke with imbalanced data. This is a Kaggle link. Let me just find what it is. As you can understand, I'm least bothered to remember the APIs and things of that sort, because I really don't want to do that. Yeah, this is what it is. I really don't want to do that because in this age, we don't need to do that. We can simply go to the internet and we are going to find a lot of resources. So there is some problem that I have done. Let me see. Yes, fit sample. Oh, sorry. Yeah. Dot fit sample. I got X and Y. And now what I'm going to do is that I can create my trading and testing data. I'm sure that is what. Okay. Yeah. I could have done this also. I don't need to do this. I don't need to do this. I can do this, right? I can just increase the training data. What about the testing data? What about the testing data? I don't think I need to do that because if I do it for the training data, that should be more than enough. But I prefer doing it for the testing data also. So let me not do this. Okay. Let me see what is the values of y. Very good. And what are the values of x? Okay, so I have x and y, and now I have this. So x dot shape. Now I have this, and if I look at wine data, and in my data, you see I had 1599. Now it is increased to 4086. Okay, so y dot shape is also 4086 in my wine dot quality, I believe. If I do a value counts and do a sum, I'm going to get 1599. So 1599 instances of all the classes were there. Now it has been increased to 4086. Okay. Now what I'm going to do, I'm going to take x 10, y 10, no, x 10, x test, y 10, y test is equal to 10 test split x, y test size is equal to, let's say, 0.3. Now I can increase my test size because I have somewhat increased the data. So random state is equal to, let's say, I don't know, 51. Okay. Now what I'm going to say, extend dot extend scale, okay, is equal to sc dot fit transform extend. Okay, and then x test underscore scaled is going to be sc dot transform, and I'm going to take test. Right. Now I have all my data. Now I'm going to fit my model. So I'm going to do svc underscore 3, which is plain and simple svc. Okay. Or maybe I can try to use, let's do something weird. Try to do this. Okay. We'll try to, we have not fit the model with a very good data earlier, but let's try to do and see what it is going to do. Fit extend, sorry, scaled and y. Okay. Now I have this model. Now I'm going to say y pred 3 is equal to svc underscore 3 dot predict and x test scaled. Okay. And then um, 1 minute, 1 minute, 1 minute, 1 minute. I think I have done some mistakes earlier. X test scaled, yes, x test scaled I used. What about this guy? Why did I use x test? I should be using this one. The accuracy is even lower. If you look at this, the accuracy is even lower. The confusion matrix should be very bad. Right? That's what I did earlier. It should be x test scale. Let's see what is happening now. Classification report, and this is going to be y test and y pred 3. It doesn't matter whether you write y pred 3 earlier or you write y test 3 earlier. Now we have a somewhat better model, not a really very good model, but at least we have the F1 scores for each and every area, where there are some cases where F1 scores are really low, like the 6 and 7. So let me see what is the accuracy score now. Y test, Y pred 3. The accuracy score is closer to 60%. We could not do much. Maybe the selection of these values is wrong. We will have to refine the optimal values in this case. But let's see the uh, confusion matrix. Okay, let's look at the confusion matrix, and I'm going to say y test y squared 3. The end, I'm going to add another bracket. This looks not really good. There are a lot of miscalculations. I could clearly see that, right? But at least we may be going in the right path, right? So why not do one thing? Let me not do this. See what is going to happen with the by default classifier. Yeah, see, it is doing a better job actually. 76% of accuracy I have achieved. I can try to where is my grid search? Yeah. You see, again in this case I did a mistake. This should not have been done. I should have actually used the scaled data, which is okay. That is not really going to matter much. But let me just do one thing. So I'm just going to copy paste one more line from the earlier implementation. So I'm going to take this and come over here and paste it over here. And I'm going to say VC3 and parameter grids and put the data. Let this fit on 250 hits, right? And then we are going to see how it goes, right? Let's see how it really goes. I'm not expecting a very, very sharp increase, but let's see how it goes. Okay. Until this point in time, Rohit, any questions? Anyone else was on this? Any questions? Any doubts?
No, no doubts as of now. I will try to run this and we'll get back to you.
Okay. Okay. Mm-hmm. It is done. Good. Let me see. Grid search dot best estimator c equal to 10, gamma equal to 1. Okay. Very good. So SVC underscore 4 is equal to SVC c equal to 10 and sorry gamma is equal to 1, and then I'm going to say SVC underscore 4 dot fit 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 10 field y 10, and then I'm going to say y spread 4 equal to SVC underscore 4 dot predict x test field, and then to wait, right? Then I'm going to say print classification report y test y spread 4. This looks really good. This looks really good. I'm just worried about class 3. That's not really that good. Precision recall and F1 score of 100% is something that I would really worry about, because that's an indication usually of something that we may have done wrong. But the accuracy has increased to leaps and bounds, right? Let's see what is my confusion metric. Y test and y spread underscore 4. Right? The confusion matrix looks very, very clean now. So you have very few points which are misclassified. I can see a few points there also. You see this point, this point. So 10, 13, 18. Okay. Then there is this 22. So 40, 42, 46. Right. And then there is this 42. Right. So 88. Then there will be 99. Right. And then these 8 points. Right. 101 and 108. So 109. 109 incorrectly classified points are still there, right? But the rest, majority, are classified really very well. The only thing that I'm worried about is this first entry. This first entry. This one belongs to class 3 actually. This one belongs to wine quality equal to 3. Exactly, it has predicted all the values. So this is a bit worrying. Okay, let's see at later stage what we can do about it. Okay, so I'm going to call this the end of this module right now. I cannot find the coefficients of SVM in this case, unfortunately, because I've not used a linear SVM, right? But we have technically proven that we have done a lot of hyperparameter tuning. We have done scaling of the data also. This is kind of a best practice that we will follow, right? And then we were able to smooth the data. We were able to upsample the data, and we were able to get a very, very nice model even out of an imbalanced data, right? We were able to do really good, right? So this is what I wanted to show when it came to support vector classifier as of now. Please run this on your end. I'm going to share the notebook and all the links and the video also. Please run this from your end, see if there are any improvements that you can do, right? If more improvements can be done, right? If some more feature engineering can be done out of this, provided you can understand these things, right? And then from the next week, we will start with one more type of ensembles which we have not seen yet. We've looked into random forest, which is really a mighty powerful thing that we have seen. But it's part of the bagging algorithm, right? Now we are going to look into boosting. So we are going to look into boosting algorithms, which are sequential in nature, but they are really, really powerful. Okay. Uh, we will still be able to visualize them because we'll come to know that under the hood, boosting algorithms will also use decision tree classifiers as weak learners. Okay, I'm not going to share what I meant by weak learner right now. We are going to explore that by the next week, right? Okay, I think that's all from me as of now, Rohi. Any questions from you?
No questions as of now.
Okay, great. Then have a good weekend, Rohi.
Yeah.
We will see. We will meet again on to Monday.
Yeah, yeah, sure.
Yeah. Thank
Yeah.
you.
Thanks for making.
Thank you so much.